Alright guys, so in this example what we're going to be doing is we're going to be looking at a full two-dimensional motion example with kinematics. So our previous example, we were really only dealing with the vector portion. That's really the most difficult part, but it is the breaking down a 2D vector into components and then putting it back together from components back into a 2D vector kind of at the end of our problem. But this is going to work through a few steps with the intermediary steps of working with kinematic formulas. Okay, so we have, in this example, we have a fish is jumping out of the water at a certain angle. Right here our angle is 30 degrees. And we know the horizontal component of this fish's velocity. So let's go ahead and highlight some of this information here. We know that it is jumping out at an angle of 30 degrees. We are looking for, we know the horizontal component is 4.4 meters per second. And we know that we are looking for the vertical component of this velocity, right? So this is going to be the first step that we're doing. Very, very similar to the previous problem that we worked with. So as always, first step, really good thing to do here, just on the side so we make sure that we know what is going on and we can visualize this. We have a fish, that's a fish, okay? And it jumps out of the water. And this fish jumps out of the water at a certain angle, right? And this angle here is 30 degrees. So as soon as it leaves the water, it leaves at an angle of 30 degrees, and we know a little bit about its velocity, right? Specifically, we know the horizontal part of its velocity once it leaves the water, right? So we can draw this here. I can do this kind of in another color, but this fish has some velocity, some initial velocity. We don't know what this is, but we know that the horizontal part of this velocity, v initial x, is equal to 4.4 meters per second. Sorry, it's a little messy. Okay, so 4.4 meters per second. What we want to find here is what is my initial velocity in the y direction? What is the vertical component of this velocity as soon as the fish leaves the water, right? So let's kind of set this up here. What we're going to do, and I'm going to kind of carry this through, just like I told you before, is we're going to be using an x component and a y component. Okay, and what I'll do here is I'll write in my variables. So here I'll have initial velocity, final velocity, acceleration, displacement, and time. And then the same thing in the y direction, except I kind of subscript them with y's so that I don't get them confused, even though sometimes my x's look like y's. Okay, so we have displacement and time. Okay, so here we have, you know what we can do, make sure that we keep this apart here. Just change this to red color. Okay, so that way we can kind of keep track of what we're doing here. So what we need to do is we need to keep all of our information separate in the x direction and in the y direction. The reason why we need to do this is because when we work with our kinematic formulas, we have to work with either x or y. We don't mix them. The only thing that mixes here is time. Okay? So in the first one, this is just like our vector example, should be fairly straightforward. We know our angle and we know our horizontal component of our velocity. We need to find the vertical component of our velocity. So let's first just go ahead and fill this in. This is what we know. So I can kind of take this here. My initial velocity in the x was 4.4. Okay, and that's pretty much all I know right now. Okay, so we'll get into a little bit about free fall and how we can fill in a little bit more of this information, but right now this is enough for us to start. So we have our triangle here looking I know essentially my angle and my adjacent side. Can I find my opposite side? So one more time. I know my angle, my adjacent side. Which formula can I use to find my opposite side? So go ahead and look through your trigonometry formulas and go ahead and choose one, and we'll see if we've gotten this right. Okay, so if you chose the formula tangent theta is equal to, my initial velocity in the y over my initial velocity in the x. This is essentially my opposite over adjacent. Tangent theta is opposite over adjacent. Then this is a good formula for us to use because we know theta, so we know this side of the formula, and we know the horizontal component. This is the only unknown thing here. So what we're going to do is we're going to take both sides, multiply by my initial velocity in the x direction. So that'll cancel out on the right side. We have on the left side here, we've got this. So now we can kind of rewrite this as my initial velocity in the y is whatever my initial velocity was in the x times the tangent of the angle that I have. Okay, so let's go ahead and plug in what we know here. This is 4.4 times the tangent of 30 degrees. Okay, so we kind of get our calculators out here. We can work through this. Remember, if you get a different answer than me on any of these trigonometry problems, probably what is going on is your calculator is not in degree mode. Okay, so I've got here 2.54. Okay, so this should be 2.54 meters per second. This is indeed my answer here. Okay, I believe so. But also I can use this now to fill in a little bit more of my tables. So you'll see we can kind of use these tables to fill in information as we're going along. So if we have, let's say, a part B, a part C, we can use the information that we know to find out even more, right? So to avoid setting all of this up again, you can have this information here copied over, and we'll be using the same information right here. Now here, I want to know what are the vertical and horizontal components of the velocity 0.6 seconds after leaving the surface of the water. Okay, so now this is where our kinematics comes in. This is what we didn't have in our previous practice problem. So here we have our initial conditions, okay? And I want to know 0.6 seconds later, what are the new components? What is the new Vx and the new Vy? That's essentially what is here. What is my Vfx and my Vfy? What are these values? Okay. Now you'll notice here that, remember, we need 3 pieces of information for kinematics, and you're going to need them in each column. Remember, they're separate, right? So I'm going to need 3 variables that I know, and 3 variables that I know in the y, and then the 4th here is the thing that we're trying to find in order to choose which formula we're going to use. So we know here that my time is 0.6 seconds. This is good. Each column now has 2 pieces of information, but each column now needs a third. We need a third piece of information. Okay? So here is where free fall comes back in. So let's go ahead and kind of invoke here free fall. Now, you'll remember last time we discussed free fall was that my acceleration was equal to negative 9.8 meters per second squared, right? This is the acceleration due to gravity. Now, gravity here acts only in one direction, right? That is downwards, but that is our vertical direction. So this value here is actually describing my acceleration in the y direction. So this is great. We can use this to fill in here, not only for this problem, but for any problem that is free fall, right? Remember, the conditions for free fall is that the fish is in the air. That's it. That's the only condition. If it's in the air, it's not touching anything, it's in free fall. The only thing that acting on it is gravity. So we can use this to fill in the acceleration in the y direction, but also we can use this to fill in the acceleration in the x direction. Now think about this for a moment. Is there any horizontal gravity? Is there any sideways gravity, right? There's not, thankfully. Otherwise it would just be chaos, right? You just fall eastward, as soon as you get up, right? So there's actually no horizontal gravity. There's only this vertical acceleration, only this vertical force that we're going to start talking about in our next modules, right? So this makes this very easy for us, because not only do we know that our acceleration is negative 9.8 meters per second squared in the y direction, we know that in the x direction we have 0 meters per second squared, right? Okay, so I'm leaving off the units here, but if this confuses you, please just let me know. We can go a little bit slower and I can include these units. I'm just being a little lazy here. So we know now our acceleration values, and this is great because now in each column we have 1, 2, 3 pieces of information, and the fourth being what we're looking for. Same pieces of information in the y direction. So because we have 3 pieces of information, we have everything we need to choose a formula. Also, as a bonus, because they are both the same, in each column we have initial velocity, acceleration, and time, and we are looking for our final velocity. This is the same for both columns, right? Initial velocity, acceleration, time. We're looking for final velocity. We're going to use the same formula in the horizontal direction and the vertical direction. We just have to keep them separate, right? So this is kind of the organizational part. This is a little bit difficult here, more so than our math, right? Our math is not so difficult, but organizing our information kind of is. So what we're going to do here is we are going to choose a formula. So if you guys go back through your formulas, right? If you haven't, make sure you download the formula sheet in the course and look through the kinematic formulas and choose one based on what we know. We know initial velocity, acceleration, time. We are looking for final velocity. So go ahead and choose which of our 4 formulas we can use there. And then once you're ready, we will go on to solve the problem together. Okay, so hopefully the formula that you looked up here is this formula right here, is my final velocity is equal to my initial velocity plus acceleration times time, right? And similarly, this is going to work in the y direction. You see just how I keep them separate here. It takes up a little bit of space, but it's very, very convenient for us to keep this separate to make sure that we don't start mixing any of these variables. Okay, so what we're going to do is let's go ahead and work in the x direction first, because this is going to be super quick. Because we have this acceleration equal to 0, this is going to be super quick. Let's go ahead and plug in everything that we know here. So VF in my x direction is equal to my initial velocity, which was 4.4 meters per second, plus my acceleration, which is 0, times time, which is 0.6. So this whole thing right here is equal to 0. And all I'm left with is my final velocity in the x is equal to 4.4. Great. All right, super quick, very easy. It's easy to work with. This is going to be the case for all of our free fall. You don't have any acceleration in your x, so my velocity is constant. It never changes. As long as this fish is in the air, whatever horizontal velocity it had when it left the surface of the water, it's going to keep that throughout its whole arc, throughout its whole path. Okay, Now let's do this now in the y direction. So we have our final velocity in the y is going to equal my initial velocity, which was 2.54, okay, plus my acceleration, which is negative 9.8. Always negative 9.8. It's not going to change. It's not going to be positive because it's going up and negative when it's going down. It never changes. As soon as the fish leaves the water, it's going to be negative 9.8 constant, okay? And the time that we're going to use here is 0.6, so you guys can use this in our calculator to find out what this number is right here. I'll go ahead and calculate this as well, so let's do this together. So we have, okay, if I've gotten this right, negative 3.34, okay? So we have negative 3.34 meters per second. So this is good. Very, very good. So now we have both of our values. We found the horizontal and the vertical components of the velocity now 0.6 seconds later. And we'll kind of illustrate what is going on here in the next part of the problem. But what we're going to do is let's go ahead and fill this in so we can kind of take these values to the next part of the problem. So here I have negative 3.34, and in my x direction I have still 4.4, just as I did in the first part. Okay, and let's go ahead and take all of this information with us. See if nothing gets left behind here. Alright, that looks pretty good. Let's go ahead and take all this with us, see if I can get rid of some of these little dots. Okay. And for the final part here, now that we know the components of our final velocity, can we find the magnitude and direction of the fish's velocity now that some time has passed, right? So the fish jumped out and now some time has passed. Now it's moving in a new direction, right? So if we kind of draw our picture again, sort of what's going on now. So in the beginning, we had fish, there it is, jumped out of the water, okay? Now, so we had a positive vertical and positive horizontal component, okay? So it was moving to the right and it was moving upward, right? Now at some time later, it's still moving to the right. We have a positive horizontal component, but our vertical component is negative. So it's moving to the right, but it's moving downward, right? So if I can draw this fish somewhere over here, okay, it is now moving something like this, where this would be my final velocity in the x and this would be my final velocity in the y. My y is downwards and my x is to the right. So when we combine these, we get this kind of angle right here. And so this is projectile motion. This is this arc that you're always going to see, right? This arc that you'll see, this fish kind of traveled in an arc going all the way down, right? That arc was caused only by the vertical part of its motion changing. The horizontal part stayed constant the entire time. So let's go ahead and find, now we know the horizontal and vertical components. Can we put this together into a triangle, right? So I'm going to draw this triangle again right here, just a little bit bigger for us. So this will be similar to our vector problem again. We're just combining our results. So we have our final velocity in the x, this was 4.4, and our final velocity in the y, this was negative 3.34. So can I find the final and my direction? So this is magnitude here, how fast is this fish moving, and direction, what's the exact direction that the fish is moving in, okay, in degrees. So to do this, just like we did in our previous example here, we have our Pythagorean theorem that we can use. So we can do VF is equal to the square root of VFX squared plus VFY squared. Okay, so I've skipped that little introductory step of the Pythagorean theorem. So if you're confused about me doing this, make sure you go back and review our previous work. But this is what it'll look like for us to find our final velocity. So to do this, we will plug in, so we'll go ahead and plug in our values here. This will be 4.4 squared plus a negative 3.34 squared. Make sure if you're doing this in a calculator, you kind of keep that negative in a parentheses. So my final velocity, so I'm going to go ahead and do this on our calculator, so follow along with me here and do your calculation to make sure we're getting the same answer. I make mistakes very often and you guys aren't here live to correct me. So if I make a mistake, you can let me know, you can send me an email. Okay, so I have a final velocity here of about 5.52 meters per second. This is the magnitude of my velocity. Remember, don't get confused by the word magnitude. It just essentially means the amount. What is the amount of velocity that I have, right? So this is telling me how fast I'm moving, and the direction is going to tell me in which direction I'm actually moving. Both of these things combine together for velocity. Okay, so to find my angle, remember, now I know all three sides of my triangle. I know my horizontal, my vertical, and my hypotenuse part of my triangle, so I can use any formula that I want in terms of trigonometry to find this angle. But I always like to use, okay, here my trusty tangent theta is VFY over VFX, okay, opposite over adjacent, which is equal to negative 3.34 over 4.4. And remember, we have to do tangent inverse of both sides, so this ends up looking like this. Tangent inverse of 3.34, sorry, it's a little messy right there, over 4.4. Just like we did in the previous example, okay, so this should look very familiar to you. And now to find that angle, we'll just go ahead and do this together, so calculate along with me. Tangent inverse of negative 3.34 divided by 4.4 should give me negative 37.2 degrees, okay? So remember, when we do this, if you get a very tiny number, make sure you check which mode your calculator's in. Degrees should be, a slightly larger number like this. And this will be it. Both of these together will give me my velocity. Magnitude and direction need to combine to give me my velocity. So remember, this negative also comes up because it is below horizontal. It's starting from horizontal, it's going downwards, right? So negative angle is downwards, positive angle is going to kind of go upwards. So that's the only reason why we have this negative here. All right, guys. So that's it. Hopefully this was helpful for you guys to see a full example worked. If you'd like me to work out some more examples, you guys need a little bit more help with this practice, please just let me know. I'll also post these notes for us. And then we can move on to doing a few more examples that have a little bit more complex situations, right? But it'll work out with the same procedure roughly every time we do this, right? All right, guys, let's get it.